Now, the latest development from Google that it describes as a state-of-the-art quantum computer chip.
Quantum computing represents one of the most exciting and transformative technological frontiers of the 21st century. While digital computers have revolutionized nearly every aspect of modern life, quantum computers promise to take us even further, potentially reshaping our understanding of computation, reality, and the universe itself. Google's Willow chip, a 105-qubit quantum processor, stands as a testament to this potential, achieving feats that classical computers could never match. In this exploration, we'll delve into the significance of quantum computing, the groundbreaking achievements of the Willow chip, and the profound implications this technology holds for the future. The quantum leap beyond classical computing. Classical computers, the backbone of modern technology, operate using bits, binary units of information that exist as either 0 or 1. Quantum computers, however, leverage qubits, which exploit the principles of quantum mechanics to exist in multiple states simultaneously. This phenomenon, known as superposition, allows quantum computers to process vast amounts of information in parallel, enabling them to solve problems that are intractable for classical systems. Another key quantum principle is entanglement, where qubits become interconnected in such a way that the state of one instantly influences the state of another, regardless of distance. This interconnectedness allows quantum computers to perform calculations at unprecedented speeds and scales. For example, while two classical bits can represent only one of 4 possible combinations at any given time, 2 qubits can represent all 4 combinations simultaneously. As the number of qubits increases, this capability grows exponentially, making quantum computers incredibly powerful for specific tasks. Google's Willow chip, a quantum milestone. Google's Willow chip is a 105-qubit quantum processor that has demonstrated the immense potential of quantum computing. In a landmark achievement, Willow solved a complex problem known as random circuit sampling in less than 5 minutes. A task that would take the most advanced classical supercomputers 10 septillion years to complete. This milestone, known as quantum supremacy, marks the point at which quantum computers outperform classical systems in specific tasks. Random circuit sampling, while largely theoretical, serves as a benchmark to showcase the capabilities of quantum computers. It involves creating highly complex and entangled quantum patterns, a task that is practically impossible for classical systems due to its exponential complexity. Willow's success in this area is a significant step forward, proving that quantum computers can handle problems previously considered unsolvable. The implications of quantum supremacy. The implications of quantum supremacy extend far beyond theoretical benchmarks. Quantum computers like Willow have the potential to revolutionize fields such as cryptography, materials science, artificial intelligence, and drug discovery. For instance, quantum simulations could enable researchers to design new materials with unprecedented properties, optimize complex logistical systems, or accelerate the development of life-saving medicines by modeling molecular interactions at an atomic level. In cryptography, quantum computers pose both opportunities and challenges. While they could crack current encryption methods like RSA, which secure everything from online banking to government communications, researchers are already working on quantum-resistant encryption techniques. Quantum computing might even lead to new forms of encryption that are more secure than anything available today. Challenges and limitations. Despite their potential, quantum computers are not without challenges. Quantum systems are incredibly fragile, susceptible to even the slightest environmental disturbances. Factors like temperature fluctuations, electromagnetic interference, and vibrations can disrupt the delicate quantum states required for computation. This fragility necessitates advanced error correction techniques, which are critical for making quantum computers viable for real-world applications. Error correction in quantum computing involves grouping multiple physical qubits to create a single logical qubit, which is more stable and reliable. However, this process is resource-intensive, as each logical qubit may require hundreds or even thousands of physical qubits to function effectively. Google's Willow chip represents a significant advancement in this area, demonstrating that error correction can outpace error generation as systems scale, a breakthrough that could pave the way for more robust and scalable quantum computers. The multiverse hypothesis and quantum computing. One of the most intriguing aspects of quantum computing is its connection to theories of parallel universes. The many-worlds interpretation of quantum mechanics suggests that every possible outcome of a quantum event occurs in a separate, parallel universe. When applied to quantum computing, this theory implies that quantum computers might be leveraging the power of infinite realities to perform calculations. For example, when a quantum computer processes a calculation, it explores countless possibilities simultaneously. The multiverse hypothesis suggests that each of these possibilities is being computed in a different universe, with the results converging in our own. While this idea remains speculative, it highlights the profound and mysterious nature of quantum mechanics and its potential to reshape our understanding of reality. The future of quantum computing. Quantum computing is still in its infancy, but the progress made so far is nothing short of remarkable. Tools like Google's Willow chip, while not yet ready for commercial use, serve as critical stepping stones toward a future where quantum technology is integrated into everyday life. The potential applications are vast, from revolutionizing drug discovery and material science to optimizing global supply chains and advancing artificial intelligence. However, the journey ahead is fraught with challenges. Scaling quantum systems to millions of qubits, improving error correction, and developing practical applications are just a few of the hurdles that researchers must overcome. Yet, as history has shown, every transformative technology, from electricity to the internet, has brought unforeseen opportunities and advancements. Quantum computing promises to be no different, opening doors to new realms of discovery and innovation. Conclusion. Google's Willow chip is more than just a technological achievement. It is a glimpse into a future where the boundaries of computation and reality are redefined. While the road ahead is long and uncertain, the potential of quantum computing to solve some of humanity's most pressing challenges is undeniable. Whether it's unlocking the secrets of the universe, revolutionizing industries, or expanding the boundaries of human thought, quantum computing represents a new chapter in our collective story, one that is as boundless as the quantum world itself. As we stand on the brink of this quantum revolution, one thing is clear: the journey has only just begun. The story of Willow is not just about a chip, it's about the limitless possibilities that lie ahead. What will quantum computers uncover next? The answer, much like the quantum realm itself, remains shrouded in mystery, but the potential is nothing short of extraordinary.